I'm gonna go ahead and say I feel like people won't do this, but I hope you all can turn your cameras on just so we can see you and can maybe get to know you throughout the workshop as well. But before I hand it off to Pratik and Michael for presenting, I just want to say that you can, or you should at least, hopefully, follow our social media pages if you haven't already. We're pretty active on our Discord. Um, as well as Facebook, Instagram, and LinkedIn. You can get more updates there as well as our mailing list. And throughout the workshop today, feel free to ask any questions at any time, either directly or you can put in the chat as well. But with that said, I'm going to go ahead and stop presenting and turn it over to Pratik and Michael.
Okay.
Yeah, I'll talk for a bit, and then so thank you, My3, for that great introduction. And once Pratik is going to get set up with presenting his screen and how to get started with the workshop, I'm going to first talk about what we're going to be doing. So this is an intro to AI workshop, so we're not expecting you to know any fancy algorithms. We're not expecting like 5 years of math and linear algebra and calculus. We're just expecting that you know basic programming and preferably some Python, and just like basically you know what a line looks like. So not expecting a whole lot out of what you out of y'all, and we're gonna be going. Oh man, it looks weird looking at me from there. But we're going to be going through a workshop to talk about some interesting machine learning models that are very popular and how they can be used in our data set, which is about breast cancer prediction. Like if you from patient information, seeing like if some whether a certain patient has a malignant or benign tumor, so if it's safe or not, basically. So Pratik, whenever you're ready, you can get started with the presentation.
Okay. So to kind of answer the question that one person had, was how do you get the actual code and the information that I'm about to present? So for the most part, what you basically do is, this is preferable for you to have a Google account, so it's a little bit easier for you. So go to that link, and there's a little drop-down menu here. And from here, what you want to do is, I posted a link on the Discord, but I'll also post the link on the Hangouts. What you basically want to do is open a notebook and select GitHub, and then give the URL that I'm about to paste here. So when you paste that URL in and you click the search button, it should, in theory, just let you see the workshop as you can view it here with all the material that you need. If you aren't seeing that, just let one of us know. And the other option you could have just done was, you could have just downloaded this and then just did a basic open notebook and clicked on a file upload option. That's another way you could have done it. You have multiple ways of doing the same thing, basically. That's what I'm trying to get at. The one thing that, if you want to get the full thing, is to consider the fact that there's some images that I have put into this presentation. They're not anything too important in the grand scheme of things, but if you want to add them, you can. For the sake of simplicity, I'm just going to be worrying about the images, and I recommend just watching me talk about them instead. Without that, yeah. Go ahead, Michael.
Yeah, so just to reiterate some of the things that Pratik has touched on, this is Google Collab notebook, the first link that he sent out. Also, if you think that you skipped a step or we're going too fast, please let us know. And yeah, please zoom in a little if someone's suggestion. So
Zoom in a little.
yeah, so Google Colab here is a way to run a Python file or basically run Python code. Normally you'd see like a bunch of Python text and like a Python file and be able to like run that on command line or something. This is a different way to do it where you can actually embed text. So instead of just doing comments to the way to document code, you have the way to put actual text and images to help better explain what the code is doing, which is a great way for presenting, which is what we have here. And Google Colab is Google Colab's is useful because it's connected to a lot of different things, such as GitHub, which is where our code base is stored on for this workshop. And if you were to link the Google Colab notebook, yes, to the GitHub repository, then you'll be able to instantly find the document that we're referring to instead of having to like look for it and then download it specifically and that whole mess. So
Yeah, I just
very
wanted to
useful.
give some options for you to be able to run the code itself instead of just looking at it. Have that little bit of interactivity.
Right.
So yeah,
All
I
right.
guess
I'll pass it back to you.
okay. So I guess I'll just start with what everything corresponds to. So what I'm probably going to do is my way of doing the teaching itself is start a very course, and then if we have the time, go back and fine tune some things. So with that, what I'm going to be doing is let's go ahead and see if I can hide all of the so view collapse sections. Okay, so the first course look through is just a matter of what the main topics that we're going to be going through. So right now we're just going over the overview, and basically it's just a matter of trying to do some fundamental machine learning models, doing some data processing, and trying to understand the logic and kind of the limitations of what a machine learning engineer has to go through when they are working with this particular problem. As we've mentioned before, Google Colab is the way that we're going to be presenting the information. You can also do it using an offline version of the notebook itself. I don't really recommend that, at least for this workshop, but you have that option if you want to. From there, we're going to be talking about what artificial intelligence is and what it is trying to accomplish, what machine learning's role is in terms of what artificial intelligence is after. And from there, we're going to start looking at the data, start pre-processing and analyzing the information that we're collecting from the breast cancer information. Once we've kind of crossed that point, it's no longer a matter of just what its relation to is in terms of the breast cancer info. It's just the model just cares about the numbers. So after this point, it's going to be a lot of math, but we'll work it through together. We're going to talk about firstly of linear classifiers. Most people are familiar with y equals mx plus b, for example, but when you're working with so many different attributes, it can be really difficult to work with just that. So we're going to do in a more generalized form to accept any number of features or attributes. Fine. After that, we're going to be talking about one of the major concepts, which is the bias variance trade-off, which is basically how do you define the amount of error that your model is producing and what difficulties you have with trying to get both bias and variance down. Then we take a small little break, just about like 5 minutes or so, to catch our breaths, to ask questions if we need to. And then we go back and begin talking about the other major concept, which is the non-linearity problem. And that basically is just corresponding to if our actual information is nonlinear, can we use a linear classifier to do a good enough job? And that's where that comes in. Finally, we talk about the big ones. So transformation models is one of the approaches that you can use to solve the non-linearity problem. And the particular implementation is with neural networks. The other way you can do it is with decision boundary models or decision trees. And again, it's another way. We'll go into more detail about that. And finally, since we only have about like an hour to talk about everything, we can't cover the whole breadth of knowledge that machine learning and artificial intelligence has. So we're just going to give you some further ratings that you can look at, mainly in the form of topics. And that's about it. So now let's start going through this in a more fine-grained approach. So artificial intelligence itself is focused around having a non-biological agent doing a task that a human being or any other biological being can accomplish at the same result in terms of maybe speed or accuracy of the prediction, or even better, based on either speed or accuracy, or maybe some other metric. So to kind of give you a visual example, let's try looking at one very well-known field when it comes to artificial intelligence, and that's image recognition. So I have two images here. In this image, what do you see? And likewise, what about this one? So it's hopefully I can get it. So with two images, can you tell me what the differences between the two are, and maybe even the similarities? Oops. So this question is kind of strange to ask, but it does have a pretty importance when it comes to artificial intelligence. So obviously in the first image itself, that is the image of a dog. And on the bottom one, it's the image of literally nothing. It's just random noise that I generated a little bit while ago, just so I can use this for the example of this workshop. And even though these two images are vastly different, and you probably couldn't even tell me what the second one was, but easily tell me what the first one is, they still have a similarity to them. That similarity being the fact that if you were to randomly generate either of these two images, you have a very, very, very low probability of that happening. Basically, if you wanted to generate this image of a dog, pixel for pixel, you would need to get 2 lottery tickets and have both of them be winning tickets. So you just got 2 jackpots probability-wise, which is the same thing as 1 image for this dog. And that in context is huge, because you have this gigantic search space of so many different possibilities of images. And somehow you as a human being was able to easily determine that it's a dog. But all a human being can do is just know information that they've probably, again, gathered from prior experiences. So that's kind of counter to what a machine can see. All they can see is just a bunch of RGB values. In other words, if you wanted to kind of visualize that in some shape or form, it's kind of like how this image here is of noise. To a machine, that's all they can really see and all they can really understand. But our goal is to find underlying patterns to exploit. Because as a human being, since I can tell you that this is an image of a dog, there must be some function out there, maybe something very complicated, but a function nonetheless that is able to classify whether or not this is an image of a dog or not. Hence, this is kind of where machine learning comes into place. So as we have said multiple times in the past, if you've ever been to any of our prior workshops or if you went to our kickoff, machine learning itself is a subset of artificial intelligence and kind of is the groundwork for how you go about and training or making an artificial agent learn. And that kind of comes down to a lot of mathematics and a lot of mathematical models that we'll be going over with the workshop here. For the purposes of simplicity and for the sake of time, I'm just going to be talking about one particular type of machine learning, in this case, supervised machine learning, in which you have a bunch of attributes and you have a known label and you're trying to get a model to be able to predict that label. And with that, we actually start talking about the actual data set. So as what we have said before, we are working with a breast cancer diagnosis data set. So if we are to look at it a little bit, basically what's going on is we want to do some data analysis of that. Is there any information from a bird's eye view that we can collect and use? Because for the model, we are basically its teacher. And we want to make sure that its information is as easily understandable as possible for it. So we want to do a lot of ways to be able to take that information, change it up just a little bit to make it easier for it to understand. And there's different ways you can do it. You can put it into particular groups of, let's say this has something and this does not. You can normalize it. So if we're working with all real numbers, you can find a way of bringing it between -1 or 0 and 1, just to make it easier for it to understand. Because again, everything is dealing with binary, so you want to make it pretty understandable for that. And then a more of a heuristic approach. In other words, you have something that maybe correlates to it, but it's not the actual true distribution of the full domain space that you're working with. And let's kind of look a little bit deeper now. So the first thing we should do, obviously, is actually download the dataset. So with this link here, which goes to the dataset that we have on our GitHub page, all I've done is basically got the URL, read the file, and because we're working with numbers and one of the columns was not already in numerical format, I've adapted it to be so. So basically what I've done here is set, okay, all my malignant information, I'm going to set that as a 1. And if it's benign, I'm going to make it a 0. From there, let's go ahead and actually look at what some parts of it is. What I've done here is just shown you the first 10. And from the looks of it, we have a lot of numbers. And me as a human being, I cannot tell you whether or not one patient is malignant or benign based on what we see here. So at this stage, we are making a machine learning model try to do something, try to do a task that a human being cannot do feasibly, or at least very easily. And that's where it gets very interesting on how we can do this processing to make it easy for them. So one thing to keep in mind is that we only want information that could potentially actually be useful for our model. One thing is that ID here is just like a patient's ID and doesn't really give us any information about the actual state of the person's cancer. It just states that this person is a patient and has this ID, and nothing about the actual cancer diagnosis. So what we can do is we can just drop that feature or that attribute or whatever you want to call it. And now we have one less thing to worry about. So let's just focus on looking at a more statistical summary of our information for those who are more mathematically inclined. The big things that you really should be getting out of this is concerning of the diagnosis column here, which is the thing that we're trying to predict upon. The main things from there is the number of diagnoses we have. So this tells us that we have about 570 patients and the mean. So because of the fact that we set malignant to 1 and benign to 0, and the number is less than 0.5, that tells me that there's more cases of it being a benign classification than a malignant one, which is, well, pretty good in a real world case. I'm pretty sure no one wants to be malignant. Let's kind of go and have a more visual representation than just some numbers that we see, because even I'm having a little bit of trouble like fully processing that information.
Also, quick note before you continue, a little bit of background on what he's using to get all these charts and tables is he's imported this data as a CSV file, comma separated values, and which is basically like a text file. And he's using important libraries to import that file into his notebook, and then being able to get these diagnostics out. So one of which is using pandas, which is great for importing different types of data files and be able to do a bunch of operations like he's doing here, which is printing out the using the describe function to print out the important data, like what's the smallest value, each quartile, standard deviation, the mean, and then next he's going to use a different one called matplotlib and seaborn to actually visualize it as a chart, so you're able to digest it a lot easier. So yeah, continue.
Okay. So as what Michael was saying, the rest of this, so this code block, all it's really concerned about is looking at that diagnosis column and having a lower chart here. So all this chart here is really concerned about is how many, so given my diagnoses, how many of them are benign and how many of them are malignant. And based on what we can see here, we see that 357 cases are benign and 212 cases are malignant, which kind of matches up with the mean value here that we got, which stated that there was more benign cases than malignant. Finally, we want to go and see and look at a heuristic. In this heuristic, we're going to be looking at something that's known as the covariance heuristic. And this is basically looking at, okay, I have these two attributes, and how closely similar are they in terms of linearity? In other words, if one goes up, does the other also go up? does one go up, the other go down, or finally, as one changes, does the other one stay roughly the same? What we're after is seeing which ones are directly correlated or inversely correlated. Because with those numbers, that tells us a little bit more information. And if they're independent, it doesn't really give us any useful information. So what I'm going to be doing is I want to find the correlation in terms of the diagnosis, because that's the thing that we want to predict upon. So what I've done here is I've gathered the normalized variances of this information and basically just showed it to you on the screen. And the big key takeaway to take from this is that all the values on the very far left have a very high correlation, which means that they tend to go in a manner that corresponds to the diagnosis in some way, shape, or form, either directly or inversely. And the values on the far right don't really have that much to go off of. They don't really follow the same trend, if you're going by that. So let's, for the sake of our hypothesis, let's say that the first 5 or 6 here are going to be useful information to help us create a classifier to do our predictions upon. And we're also going to look at the last couple ones just to see whether or not this particular heuristic actually gives us some useful information to also consider. And again, one thing to keep in mind is that correlation does not imply causation, but it's still a heuristic, and every heuristic can help us get a better idea of what we are after. And from here, this is a kind of a point of no return. When it comes to machine learning models, they don't really care about what one particular attribute necessarily corresponds to. All that it sees is numbers. There's only one exception that I'm stating here, and that's just I want to prove my hypothesis, whether it's right or wrong, and see how well it holds. So I'm going to go ahead and talk a little bit about the first main classifier, in this case, a linear classifier. So most people are familiar with linear regression, or an equation like y equals mx plus b. But the problem with that particular equation is that when you're working with so many attributes, you need to have a generalized form of representing a line in multi-dimensional space. And basically, that's where a little bit of extra math comes into place, where you utilize matrices to represent your different components. But at the end of the day, it's just a generalization of what you already know. So for example, if you're going by the y equals mx plus b idea, this here, this W matrix is just a weight matrix, which acts like a slope for all the different dimensions that you have to work with. With mx plus b, x is only in one dimension, so we need to account for all of those possibilities, all those different attributes. X itself, instead of just being one dimension, it's now n dimensions, where n is the number of attributes that this particular instance or patient has to work with. Finally, b acts as like our bias or our y-intercept, and it moves based on whatever it's been set to. Finally, we have the y, which is just me represented with this function here, and it's output and it's equal to a matrix of size m by 1, where m is the number of distinct labels. So in this case, m for our particular example will be 2, because 0, corresponding to malignant and 1 corresponding to benign. There is a simplification that you can do when you're working with binary information. So in this case, you can just say that since you only have 1, you can just make this like a single value instead of a matrix. But for the sake of simplicity, we're just going to keep it like this, since it kind of goes into the flow of the rest of this workshop. The thing is, this is still not a classification task. All we've done is just mapped and generalized a regular line. So to make a classification task, we're going to consider it in terms of a threshold. So as long as our function f of x is greater than a particular threshold, we're going to classify that value as 1. And if it's not, then it's going to be 0. So to consider it in a more visual sense, I've gone ahead and brought up a little visual example. So basically, with what we have right now, our threshold is basically this little dashed area here. And every value above this is one class, and everything below it is another class. And the goal is I only know a couple dots. So there might be a couple dots like just above this line here. So like some here and a couple dots down there. My job is to create a line that best works not with the information that I know in my sample space, but in a way that can work with the entire domain, even if that domain is infinitely large. From there, we're going to talk about more about the implementation aspect of it. And this comes back to making sure that we can hit a certain threshold. With the threshold itself, since we're trying to get it to where we're working with a lot of binary information, just because it's really easy for a machine to work with that, we want to kind of change all the numbers into either does this, for this particular patient and for this patient's particular attribute, does it exceed or not a particular threshold that we set? And that's kind of where we need to do a little bit of pre-processing. We're still only looking at it in terms of numbers again, because we've already passed the point of no return when it comes to the actual data set itself. We are just concerned about finding a way to make it easy for our model to understand it. And the way for it to understand is binary. For the threshold itself, what I've basically done is, since most of the data kind of works out to look like a bell curve, most of the weight or most of the information tends to be around the average point. So that means that we can set a threshold to be the average between the largest value for that particular feature, given that that person was benign, and sum it up with the same feature, the maximum of that feature, given that it's malignant, and then just divide it by 2, so that we hit that midpoint, basically. And that acts as a threshold. This little bit of code here is just me defining said function there. And now we want to actually show the visualizations. One thing that I'm doing here now is I've created a list of attributes. And this is basically just a couple of the attributes that I said that we wanted to test our hypothesis on, for those that had a really good correlation, and then these that don't really correlate and are kind of independent of the diagnosis. From here, we go ahead and plot everything out. So we have 1, 2, 3, 4, 5, 6 good ones, and then 3 bad ones. And from the first 6 here, they tend to do pretty well overall. The very first 2 here, in fact, do exceptional and have a very clear distinction between them. There is some outliers here and there, but for the most part, everything is really cleanly shown. If we look at the last 3 here, there's a lot of overlap between the 2. In fact, this kind of cuts right down into a really big portion of it. So from the looks of it, based on what we can see here, a linear classifier seems to be pretty well suited for our particular task. So with that said and done, while we haven't done the actual changes, we should probably do that now. And that's what I've done here. And this little bit of code that I've written up, basically what I'm doing is that for each of the attributes that we're looking at and examining of a patient, we go ahead and calculate a threshold. And then for everything that exceeds the threshold, we set its value to be 1, which means that if it's 1, that means that it's better, it's above it. And likewise, if it's not, we set it to 0. From there, we want to make sure that we do a proper training of it, and we actually teach the model what to look out for. And since we want to see how well it performs, we also create a test split, and we see how well and validate its performance based on that. We proceed to then create the model, train it on our information that we have split up properly. And finally, we check a classification report to see how well it does. There's a lot of information that I've put up here, and for the sake of simplicity, we only really care about the accuracy for this workshop itself. The other information is also important, but we can talk about that later once we get an even finer comb to go through that. So what we have right now is pretty good. 89% is pretty high up there, but the question is, there's always a possibility that we can do better. And this comes into the first problem that we have, and that's the bias variance trade-off. So let me scroll down a little bit. Am I going too fast for you guys? Should I slow down, or are we at a good pace? Just to kind of get an idea of things. Okay, cool. So with the bias variance trade-off, this comes down to the fact that we are only able to see a very tiny, tiny, tiny sample of the entirety of the domain. And because of that, there are 2 points of main error that we have to consider that we can potentially manipulate, and one that we can't really do anything about for the grand scheme of things. The first one is bias. And bias just comes down to being, okay, I, as the engineer of the model, have made an assumption. The question then becomes, is my assumption a good one or a bad one? And for example, one thing that you can say is, okay, so if our data set is not linear, but we assumed it to be the case, that tends to make our overall model not really work out in our favor. And with that, we kind of don't really utilize the full extent of the information that we can do, because we believe something so hard that we just don't care about the results well enough for it to matter. The other end of the spectrum is variance. So with variance, it's basically the fact that since you have so little data, that means that your variance overall could be very big. And with that, even though you have so little, you want to get the most out of it. You want to get every single data point to be 100% accuracy when you're doing your training, because why not? You want to use everything, right? The problem with that is that your small data point that you have does not necessarily represent the whole thing. And if you try really hard to try making it work with that, you might fail in trying to map your particular model for the full thing. That trade-off is kind of shown with this image here. As your bias goes down, your variance goes up, and likewise vice versa. And there's a little bit of extra here. Even if your bias and variance reaches at its very minimal point, you will still have your total error being a little bit higher. And that just comes down to noise. Noise is something that you can't really get rid of. And you can also think of it as like outliers on the information that you have. It kind of sucks when you have it, but there's no really easy way to really work with it. You could try to determine if it is an outlier or not, but that's a topic that's a little bit more advanced, and we'll see if we can maybe talk about that in a future workshop. To get a more visual example of what's going on here, I have done a little demonstration like so. So let's go with this. Just to make sure, so let's look at this here. So I have some true function here, which is the actual representation of our distribution. I also have some noisy data, but I'm not telling you what that noisy data looks like. It's hidden from you. You don't know that at all whatsoever. All you know is the sampled knowledge that is represented by this black ring here. Anything and everything inside of it is information that you have collected. If we go back to assuming that we have a linear classification of the information and make that assumption, we can get a model that looks something like this. We've been able to properly classify all the blue here to the best of our ability. There's a little bit of problems with our red. We didn't properly classify that. If we assume that blue means past the threshold and red doesn't. So all this red here doesn't really work out, but we still get this much here, which is not bad. The problem is that this particular model isn't really utilizing the best of our abilities to account for the data that we were given. And worse, if we actually look at it from the whole domain itself, we can see that a lot of this upper region of red is classified as blue. Likewise for all of this. And while there's not a lot of blue that's been misclassified, it's still a pretty significant amount. Oops. So this is an issue of when you have something known as underfitting, or when you're not really utilizing a classifier to the best of your abilities to match the general shape or the function to how it's supposed to work out in the grand scheme of things. Of course, we can't really do anything about the fact that we have so little data. That's why we try to do what we can. The other end of the spectrum is where you try to have a model that basically does as close as possible to 100% training accuracy and not necessarily test. So the example for that would be something like, let's go ahead and turn off the line, for example, here, just to make it easier. Let's say that we have a model that tries to do just that. So if we have a classifier that goes to the very edges of what we can see in the red, so literally everything, even this little crevice here, go around the blue, and then go out like this. So basically, we literally only focus on making sure that whatever classifier we have works with the red, and everything else that's not inside of it is just blue. With our particular scope of things, it works. It gives you 100% accuracy. The problem is, again, we don't know the whole thing. And the whole thing may not just work out for us in that case. And in that case, we have a model that's overfitted. In other words, it's too reliant on what we can see from our sample and doesn't really do a good job when looking at the grand scheme of things. So, of course, we want to find a way to find a nice balancing point. And hence why we try to come up with an algorithm that is both have low bias and low variance. So for something like this could be the case. So with this particular example, we do get a good amount of the blue. We do get from both the noise and from the actual true function. And we do miss out on some of the red, and we do get some of the other red. But the most important thing is, if we look at it from the grander scale of things, this model does actually really well when it comes to the true distribution function. And something like this is kind of what we are after when we're designing our models to be as good as possible. With that, I think what I'll do is I'll just put on a 5-minute break so that we can get time for any questions. If you want to go use the restroom, get some water, that's fine as well. I'll just come back to it then. You can also just ask me questions if you have anything, and I'll be here willing to answer them. So yeah, let me go ahead. See. I'll just put on a timer for. Oops. Okay.
So Thomas Kang asked, will we also have future machine learning and AI workshops that deal with data science and engineering with Python, something I gained a strong passion in? Yeah, we'll have more workshops, different types of workshops. And so actually, let's do, during this quick break, let's have a little poll. What type of workshops do y'all want to see? Do you want to see more stuff like this, where we take a close look to taking a look at the data and analyzing it using different libraries? Do you want to see like a specific type of machine learning model that you're interested in, or deep learning? Or do you want to see like different concepts like financial data instead of biological data? Or do you want to see image data or text data instead of anything else? What type of workshops are y'all interested in?
Another way of asking that question is, oh, sorry, go ahead.
I was just going to say that, like, in addition to all those things, we also want to know if you want like more hands-on stuff, yes, or maybe like series, maybe of longer workshops. Because I think one bigger thing that we're really trying to figure out this year is just with everything being online and stuff, just how best do we make sure that our attendees, like, aren't confused, but they can follow along with, trying to get all the levels, or I guess trying to accommodate as much as possible. So yeah, any feedback would be much appreciated. Let's see, I think we had some responses to deep learning.
Data analysis, ML,
No,
deep
that
learning
works.
models, different data sets, image text, etc. Okay. So one thing that I guess with stuff like that, for someone who's trying to teach the material, those are very big words that you're telling me. And when most people think of that, yes, these are buzzwords, and that's the case. But when I got my start, I was looking more on what applications did I find really interesting. So what got me into machine learning was self-driving cars. I found that really interesting. I didn't know how a car could do it, but by some like magical being was able to make a car move without the need of any human assistance. What you guys have told me is the major name behind it. But I want to know what particular thing did you find interesting that so happened to also be within the realm of machine learning or AI? Like, did you want to know why Google keeps on asking you for image, like verifying why this is like all the stop signs, whether or not this is a crossroad or something like that, or maybe how spell checkers work. So I think a lot of people may be familiar with Grammarly. How is it able to know and utilize its AI to basically say, oh, here's a recommendation. This word seems misspelled. It's kind of those stuff that I find more indicative of what you really want to learn rather than a big concept. Because the problem with saying machine learning is that even though it may seem niche itself as a concept, just because there's so many things you can do with computer science, there's still a huge breadth of knowledge that machine learning and AI in general has to offer.
Yeah, I agree with Pratik. I'm gonna quickly steal your screen and share something, if I can find it.
Do you want me to stop sharing?
No, I think I can just steal it from you, actually.
Yeah. We have about a minute left, just to keep in mind for the break.
Think I got it. I think I just joined your screen. Good. So, if y'all are able to see my screen, I'm on a website called AI Experiments. Just like Pratik said about some interesting um, things that got him interested, just like self-driving cars. I like to take a look at this once in a while and see a bunch of cool things that Google's worked on, just applying different machine learning attributes. So let's take a look at this one. So this is a you can take a look at this yourself. Just look up AI experiments or experiments stuck with Google. Actually, I'll just put it inside of the chat here. And you take a look at this yourself. You can take a look at the video, but it's literally how an application where you can draw. If you ever played the game Scriblio, it's kind of like that, where you draw something and then the AI takes a look at what you drew and tries to guess what it is. And here's like from the thumbnail, you can see it's just like the image of or the preview, I guess, image of bike that they're drawing, or an image of bear, and they guessed it in 20 seconds. Pretty good. And I think this is the link to their GitHub, I believe. Oh no, I think it's just more things related. So yeah, I like to take a look at a bunch of these different types of projects that people have made. There's another one about music, where this one you can actually whatever notes that you type, whatever notes that you play, on like your keyboard, then the AI will try to match it by playing complementary notes at the same time, and y'all try to play a duet sound. Even if you have no experience with music, it'll still try and help you out and create a good melody. So a lot of machine learning projects like and deep learning projects like this gets me motivated to keep going in the field.
Okay.
And I'll stop sharing my screen, and Pratik can go back to if
Okay.
our break's over. Yep.
So the next major concept that kind of goes in hand with the bias variance trade-off, and I kind of hinted at before, is the non-linearity problem, also known as the XOR problem. So let me give you guys this little link to kind of set the stage for what the question is about. So I've just given you a little basic Desmos link. and it corresponds to, and there's 4 points, and your domain is basically distilled down to only 4 points. The question then becomes, with these 4 points, can you cleanly separate all the blue onto one side and all the red to the other? And this is the first kind of major point in understanding the issues or one of the flaws of linear classifiers. So if we were to take that to ourselves, if we were to use the line tool, it doesn't really matter where I put the line. So if I were to put it here, I can get kind of the red, or I can kind of do it well, but like the best case scenario I can do, no matter where I put the line, just by the little shadow that's showing me, is I only get a 50-50 chance at best to do a proper classification of it. So if you only have a 50% chance, then why would you spend all your time training a model that only does better, or even sometimes equivalently, just by a little bit, to just flipping a coin? And that's kind of where we have to think about, okay, so obviously the answer is no. I've written out a little bit of a proof if you want to get the more mathematical assertion behind my statement itself. We'll go back to that if we have time. So now it's a matter of, okay, we know that linear classifiers can't work with everything. So what can we use that's not a linear classifier and get the job done? So the first one we're going to talk about, and the big one that most people rave about, is neural networks. So with neural networks, we're only going to be focusing on one aspect of them, and that's trying to make sure that whatever output we're getting matches kind of similarly to what the function represents. So in this case, we know XOR cannot be linearly separated, cleanly at least. But if you're familiar with logical gates, if you've ever played Minecraft, or maybe have a little bit more experience, maybe taking a discrete math course, you're probably familiar with some of these. The OR gate is basically if either of your inputs is 1, your output is 1. The not and gate is if any of your inputs is 0, then you get a 1. And the AND gate is if any of your inputs is 0, then your output is 0. One thing to keep in mind is that AND here is linearly separable. You can just draw a line so that you just have only that 1 point correspond to the blue region, if we consider blue as like 1, and the red region corresponding to 0. So the question then becomes, okay, we want AND to kind of be the final ultimatum to kind of deal with and try to make it linearly or logically equivalent to XOR. The question is, though, we want to set up our inputs to AND such that it makes a logically equivalent to XOR using these other 2 logic gates. And do you guys have any ideas on what we can do for this before I just reveal the answer? I think I'll give people like a minute, so it's 6:54. I'll just say 6:55, 30 seconds. That should be good enough amount of time. Maybe, yeah, we'll just go with that then. I'll say 6:55, 15. I don't know if my messages show up here. I'll just stop at 6:55, that'll be easiest. Yeah, let's just do 15 more seconds, I think. $13, $14, $15. Okay, so I don't know if I necessarily gave you too little time, but it's not that bad. So with XOR, you can the logical equivalence of it based on these three here is basically the input of AND is just the two OR gates itself. So you have the OR gate where you give it the inputs A and B, and the not AND gate where you just give the inputs of it to be like that. So from there, we want to kind of visualize how the different gates will look like in a manner similar to us trying to create a linear classifier to do all the three gates. So for the OR gate itself, it's a pretty basic way of doing it. So again, as long as one of the inputs is 1, we know that our output will be 1. So with that, what we can just say is that, okay, so we can set our threshold to be 0.5 and our weights to be 1. That way, as long as one of them are here is 1, we know that it exceeds the threshold because it's just 0.5. Even if this one is 1 and this one is 0, it satisfies the threshold. And you can do every combination except for 0, 0, because, well, 0 times 1 plus 0 times 1 is obviously 0. And of course, 1 times 1 plus 0 times 1 is 1. And of course, if you have 1 plus 1, that's 2. It exceeds it. That's OR. Let's go with not AND. I've just kind of set it to NAND. Doesn't really matter what I call it. This one, again, it's corresponding to as long as you have a single 0, your output is 1. So we care about making sure with that. So something along the lines of this is what we're kind of after here. We want to, instead of making a concern of just ones, we want to kind of go in reverse of the OR gate. In this case, we've set the weights to be -1, and we set the threshold to be a large negative value, in this case, -1.5. With the way that we've done it here, the only way we could have generated -2 is if both of these are 1. Because 1 times -1 is -1, and then you add that to 1 times -1, which is -1. So now we've satisfied what a not AND gate is. Finally, we have the AND gate. And again, going back to this, the only time, as long as we have a single 0, your output will always be 0. And it'll be 1 otherwise, like so. With this gate itself, we just care about kind of the opposite of the not AND gate. So we just flip all the weights and the threshold. So instead of -1, it's 1, and instead of -1.5, it's 1.5. And that's our AND gate. The final step is now just combining everything together. And that's just a matter of literally connecting the dots. So with our completed XOR components, it's now just merging everything together. So if you see here, we have the OR gate on the top, the NAND gate on the bottom, and the AND gate like here. And with that, we have successfully created the neural network itself. Any questions before we go into the actual implementation? I guess I'll say maybe a minute will be good. So I'll start now, and once it's 7 o'clock, we can go further. Oh, can you resume presenting?
Also going to cut in super quickly just in case anyone has to leave early because I do know it's 7 and we initially meant for it to be 6 to 7 p.m. Before you leave, we would really, really appreciate it if you could just fill out the quick feedback form that I put in the chat, just so that we get an understanding of what you guys felt about the material and how better we can improve events. especially since this is the first workshop that we've done in a while. So yeah, that would be great. Thank you.
Okay, so I guess I'll just go with the implementation. So with the neural network, okay, it doesn't really matter. So with the actual implementation of the model from a theoretical point to Python code, it's again pretty basic. It's just a matter of we create our train test split, we define our classifier model here, we train it on the data set that we've just generated, and then finally we go about and we'll see how well it does. And we went from an 89% accuracy to a 95% accuracy. So that's pretty good. With that said and done, that's kind of more or less with neural networks itself. There are some kind of flaws that I want to go over with neural networks itself. The big ones is the fact that, well, the big one for the workshop itself is the fact that we kind of glossed over how a neural network adjusts its weights accordingly. The fault in the XOR example is the fact that we kind of know the whole domain. And in reality, what you're going to be working with more is that your initial weights for each of the lines is going to be a random value. And to adjust the weights requires a little bit of knowledge in calculus, which we can't really cover for the sake of an introductory workshop. We will try to see if we can provide some materials maybe later on to help you learn about that. We've kind of hinted at it in the further readings if you looked at it already. But again, it's not anything too complicated, at least from my point of view, that you can probably learn this really quickly. Besides that, coming back to the bias variance trade-off, what we've basically said and done with our particular model is that this model is a lot more variable. Since we're not just looking at one dimension, but now we're considering it in nonlinear form, we can make our model shape a little bit better towards our actual data set and with the number and the information that we have. Again, we're sacrificing the variance a little bit in terms of getting that low. It's now just a little bit higher, but the trade-off that we made has shown it to be pretty good results, as we can see with the 95% accuracy on the test data set. Of course, we don't know necessarily how the whole domain looks like. We can only assume it looks similar to what our sample looks like. But this is still really good, I would say. With that, I think we'll go ahead and take, let's say, I think, okay, so I covered a lot of information. So do you guys want to do another small little break, maybe 5 minutes, open up for a longer discussion for questions and giving you more time to go through the material yourself of what we just covered, or do you just want to move on to the last classification approach? Kind of confused of what a neural network is. Okay. I was wondering why I didn't get, okay. So what a neural network basically is course, so you can think about it as a series of multiple linear classifiers, as what I've shown you here. So what we've basically done is that the OR gate here is linearly separable, as what we've shown here in the example. The not AND gate is linearly separable, and the AND gate is also linearly separable. Most importantly, the AND gate is. The other two here doesn't necessarily need to be, but it just so happens to be the case. What we care about when it comes to the actual model itself is that on our input layer, so in this case, the A and B, that's just whatever attributes that we are giving into the model. And then our final output one is just a matter of, okay, this is going to be my output layer. This corresponds to whatever the number of different labels that we have. Since we are working with just binary, we can just say it's just one or the other. This middle here, or the intermediary layer, is also known as a hidden layer. And the whole purpose of the hidden layer is to extract strong features, or in other words, underlying information from our original input. In this case, that underlying input is whether or not our A and B values satisfy the conditions for or and satisfy the conditions for not and. Because with those strong features, we can then continue on and check further from there. So we know a couple things about our information. We know that it satisfies or it doesn't, and we know if it satisfies not and or it doesn't. And from there, at the very end of all this checking, of trying to extract out underlying information, just like how a human being can tell that this is an image of a dog because you can look at the structure of its face, or you can look at its ears, or you can look at maybe even the snout, for example. You get these strong features and you say, okay, this is an image of a cat or it's an image of a dog, because both a cat and a dog have those same features. But there might be something that just takes you in one direction. Maybe it's the shape of the eyes. It could be the stature of the animal. That's kind of where this middle layer is coming to. Does that kind of answer your question, or are you asking it more in terms of the mathematics behind neural networks?
Okay. Yeah, so I try to give my own explanation without trying to interrupt you to Neha, and let me know if like either of our explanations works, but I kind of just try to say that basically tries to look at the no problem, Neha. So I just try to explain it as like someone that's trying to take a test on like, I don't know, economy, and they have no idea what the test what economy is, but they have a bunch of tests, or it's like the SAT. You've never taken the SAT before, and you try it for the first time, and you get like 800. It's like, oh, that's probably bad. Let's try some different things and learn some different things to make it better. And you take it next time, you get 1100. It's like, oh, great, I did a lot better this time. And then you keep going and keep going until you finally get, I don't know, 1600. I guess that's what it is now. So, yeah, that's kind of how generally it would work without all the confusing math behind it.
And I think we'll spend like a couple more minutes, maybe like 3 minutes until like 7:10 for any other questions. If you don't have any, you can just get some water or whatever you want to do to relax. Me and Michael will just be ready to answer anything if you have one.
Yeah, so is there any other questions about what Pratika's gone over so far in the presentation?
It's fine if you don't understand something, we can just go over it pretty quickly, just so we can kind of figure out where you stand and explain that maybe we missed one thing that wasn't as clear as we thought it would be to you. I'll just have like one more minute, then we can move on. Let's go back to Okay, so I guess I'll just start off with the last classifier. So we mentioned a classifier that focuses on manipulating the actual input itself to work with an eventual linear classification model with some intermediary steps that we go through. There's another way that you can go about it. So instead of you trying to manipulate the positions of this by using transformation algorithms, what you can do instead is, so basically, if one line isn't really enough to do the classification task, you just add more lines. Now you have the situation where everything in this blue area, everything within this particular quadrant corresponds to blue, everything here corresponds to blue and red respectively. And that's kind of where decision boundary models come into place. Our particular implementation will be focused on something known as a decision tree itself. So we go ahead and do what we've always done. We go ahead and create our training test split. We go ahead and train the model. And before we do check the results of it, let's see the underlying structure. So what we have here, there's a couple ways you can think about it. You can think about it as like an attribute hierarchy. For me, what I'm going to be thinking about, it, as the name kind of implies, as a decision tree, where what that basically means is that at the beginning of every point, if I can kind of zoom in a little, maybe do this. The lines don't really work in our favor, sadly. But anyways, so if we look at the topmost location, this corresponds to a decision being made. And again, it's dealing with thresholds. So it's just a matter of, okay, for this particular attribute that this particular instance have, is that number less than or equal to this value here? If it is, or it's true, we go to the right side. And if it isn't, we can go to the left. And we continue with that pattern. And notice that as we keep making these distinctions, the color either changes to something else entirely, like in this case here, or it just becomes a darker shade of what we got here. So for example, if we go to the right side of this, we can see that the color changed to be something around a blue hue. And one thing to keep in mind is that once there's just only that particular value there and the other one is just 0, we just stop there, because there's no reason for us to go any further, because this is now just a single pure node that we have in our structure. Likewise, here we got it happening again, where we have 2 pure nodes, so there's no more reason to go any further. However, there are cases in which, even if you go all the way down, you still have some impurity. So for example, with something like this here, there's 75 benign cases and 2 malignant. And the reason why we don't go any further is to handle the case of our model not overfitting. One of the main issues when it comes to this kind of classification model is that it tends to really want to overfit. And the main way that you can stop it is by setting a specific depth. And if you ever reach that depth, you just take a simple majority, and that's the label that you place at that node. So basically, everything down here is treated as a leaf, or the end of the hierarchy. So even though that this is not pure, we still go with that classification. Likewise, for this guy over here, this one here, unfortunately, is not, it's pretty close to a 50-50 shot between the two. We can't really do anything about it, but this might just be an outlier, as we've mentioned before. And if that's the case, then that's good for us. Finally, let's go ahead and see how well it performs. So again, we do the same thing as we always do. We get a classification report. And this model does even better than our neural network. It actually has a 96% accuracy, which is, of course, not a lot in when you compare it from 95 to 96. But that's still a lot. That's actually a really big change for how little we've actually done. All we have done is just change the type of model, and it's already improved by a little bit. This could be within a reasonable amount of standard deviation, of course. So we always want to make sure that we keep on fine-tuning our information and doing the best that we can. With that said and done, that's basically the majority of the actual workshop and the material that we have. We do have some further topics that we would recommend you guys looking at. Unfortunately, we don't have any direct links to it. We'll probably provide something of this sort in our Discord sometime in the future, though. But basically, these are the big things that we want you to kind of consider as material to consider beyond just the workshop. So with what we've done here, it's just mainly been focused on supervised learning. But there's other things that you can do. You can do unsupervised, semi-supervised, and reinforcement learning. Some people were asking about data science and data engineering. So one big concept that comes to mind when it comes to like that is something known as principal component analysis. When it comes to trying to optimize and trying to get as much value from your data as possible and trying to maximize your accuracy or minimize the amount of error that you can have, understanding gradient descent and the calculus and the derivatives behind all that stuff is really important. If you actually want to go ahead and try doing one of these implementations, such as the decision tree itself, look into something known as the ID3 decision tree algorithm. That one kind of focuses primarily on strictly binary attribute values and class values, but it gets the good idea of what you can get from that. This particular algorithm and any algorithm for decision trees really has some connections to recursion, which is a concept that I can't really expect a freshman to know necessarily. I expect it maybe a sophomore, but again, it's still a very interesting thing to look at, even if you don't necessarily have the full breadth of experience. Finally, with neural networks itself, which is the big one, is the idea of backpropagation. And this is how a neural network actually, quote unquote, trains. It's basically your weights at the very beginning are some random value. And when you go ahead and do your training, you pass whatever inputs you have through the transformations, and you get out some output. From there, you compare it to some metric of some sort, maybe an error function, for example. And based on how that error function looks, you update the weights going from right to left, which is the opposite of left to right, and that's how the whole action of neural networks work. Of course, that's a very broad explanation, and I would recommend you doing some of your own research into that field. So yeah, that's really about it. Let me see what you guys said. As for code syntax for machine learning, are there any logically similar for unsupervised, supervised, principal component analysis, and semi-supervised learning? That's what I've experienced from my own coding learning. So when you're saying code syntax, can you clarify what you mean by that? Is it just a matter of the model that you're using? Because one thing to keep in mind is that okay, that's the feedback form. So when it comes to code syntax, that kind of depends a lot on the library itself that you are using. The one that we've been using is known as scikit-learn, and they tend to have a pretty uniform way of defining its particular algorithms. Are you more talking about not maybe code syntax, but in terms of what their purposes are and what kind of questions that those particular learning paradigms are focused around?
I was aware that they're all different in a way, but I was just wondering about the code syntax based on the library, like scikit-learn or Seaborn.
Okay.
I think I used one of those two in my personal learning, and then I kind of found them like a train test split similar.
Okay. So with stuff like that, so the language, so let me ask you this. So
let me give some time for Pratik to think about his answer. And before that, I'll say thank you for coming to the workshop, because it is 7:20 now, and I understand if you need to go eat. I'm getting hungry myself, and you can go ahead and first, before you leave though, please take a look at the feedback form and fill that out so that we can improve our workshops, what you liked, didn't like, and how we can change it up. And please recommend some more topics to for the workshop, either in this chat right here or in our emailing us or in our Discord, which you haven't mentioned. Sanjeev, if you're still here, please get the link for Discord and put it in here just in case. And but that's about it. If you have any other questions though, and you want to stay in here for a little bit longer, feel free. But I'm gonna officially stop the recording right here, and I will say thank you so much and have a nice night, y'all. Hope you learned a little something from this workshop.